Hi Year 11, this is our 5th lesson for the topic of functions, and this is for the International Baccalaureate course, Analysis and Approaches. In this lesson, we're going to look at inverse functions. An inverse function is one that undoes a function, and this is how we write it. We write f, and in the power position, we write -1 of x. But this is what we say, f inverse of x. This is what it does. If we have a function that turns apples into lemons, then if we put lemons into the inverse function, we should get apples. Here's another example. If our function turns ABC into 1, 2, 3, then our inverse function should take the 1, 2, 3 and turn it back into ABC. Now we've seen inverse operations before. Addition and subtraction undo one another. Multiplication and division undo one another. And to a certain extent, square root and square undo one another. You've also seen an inverse function before with trigonometry in years 9 and 10. If you wanted to solve sine beta equals 0.5, you would find inverse sine of 0.5 on your calculator, and that would give you 30 degrees. Now we form the inverse relation by interchanging x and y, making y the subject. So suppose we have y is equal to 3x, then we switch the x and the y, and then we proceed to make y the subject. And so y will equal x over 3. So this is the inverse relation of y equals 3x. Now if this new relation is a function, which this one is, then it is called the inverse function, and we use this notation. Now using our function notation, the inverse function of f of x equals 3x is f inverse of x, which is equal to x on 3. Let's test this out. I'm going to substitute in x is equal to -1. So f of -1 is -3. Now let's work out f inverse of -3. It's -3 over 3, which is -1. So I've ended up with what I started with. Now a function and its inverse are symmetrical about the line y equals x. So here we can see the function, and here's the inverse function. Here's an example, sketch y equals 2x minus 1 and its inverse function. So we'll start by switching x and y. Now let's make y the subject and divide by 2. We end up with y is equal to x plus 1 all over 2. Now if we sketch both of those lines, we can see that they are a reflection of one another in the line y equals x. You might have noticed I was really careful with my language before, and I said that we form the inverse relation because not all inverses are functions. If the inverse relation is not a function, we don't use this notation. Here's an example. If we've got y equals x squared and we switch the x and the y, when I make y the subject, I get y is equal to plus or minus root x, and that's not a function because there's two answers for many x values. And indeed when we graph it, it's still reflected in the line y equals x, but this is not a function because it fails the vertical line test. Now remember that there are 4 basic types of relations. There's one-to-one, one-to-many, many-to-one, and many-to-many. Now which of these are going to have an inverse function? Think about flipping or reflecting them over the line y equals x. These two have an inverse function. If we reflect either of these graphs in the line y equals x, we end up with a function. Now the basic rule is a function's going to have an inverse if it passes the horizontal line test. That means any horizontal line that I draw is going to cut the graph in only one place. So I mentioned before that a function and its inverse undo one another. So it stands to reason that f inverse of f of x will be equal to x. If I put x into the function and then I do the inverse function of that answer, I should end up where I started. This is also true. F of f inverse of x is equal to x. So let's check that out. Show algebraically that f of x equals 2x plus 1 and f inverse of x equals x minus 1 all over 2 are inverse functions. So f of x is equal to 2x plus 1. Let's take this output and substitute it into f inverse of x. And we end up with 2x plus 1 take away 1 all over 2, which is 2x over 2, which is x. Now there are some implications for domain and range. When we interchange the x and the y to obtain the inverse function, we swap the domain and range. Have a look at this diagram. Here's the domain, goes into the function, out comes the range. The range of the original function goes into the inverse function, and out comes the domain of the original function. Let's look at an example. Y equals x squared has domain x is an element of the set of real numbers and range y is greater than or equal to 0. Let's write the inverse relation and find its domain and range. Now we just did this. Y is equal to plus or minus root x is the inverse relation. And the graph looks like this. What's the domain of that graph? Can you see that it is going to match the range of the original function? It's x is greater than or equal to 0. And the range, well, that's all real numbers, isn't it? It matches the domain of the original function. Now, if a function fails the horizontal line test, what we can do is restrict the domain to ensure that we have an inverse function. So suppose we've got f of x is equal to x squared. The inverse relation is y is equal to plus or minus root x. Let's restrict the domain of f of x, that's this green curve here, to be x is greater than or equal to 0, so just this part here. So f inverse of x, which is the positive square root, has a domain x is greater than or equal to 0 and y is greater than or equal to 0. Now you might have asked, well, why did you restrict it to x is greater than 0? Could we have done x is less than or equal to 0? And the answer is yes. We choose a monotonic increasing or monotonic decreasing section of the original graph, and that just means always increasing, always decreasing. So we could have chosen that part there or this part here. It's an example. Restrict the domain of f of x is equal to 2x minus x squared to make an inverse function of f of x. So I'm going to start by switching x and y. Now, you'll notice we don't have a y. This is y. So we're going to do x is equal to 2y minus y squared. Now I'm going to take all of this over this side and the x over this side because I want y squared to be positive. I'm going to complete the square. Find the term in y. Here it is. The coefficient is negative 2. Halve it gives you negative 1. Square it gives you 1. I want to add 1 to both sides. Now complete the square. Square root both sides, and you can see how I've included the plus or minus. Y is equal to 1 plus or minus the square root of 1 minus x. Now that's not a function, is it? It's a relation. So we need to restrict the domain. Now it looks like this red curve here. So we can either choose that bit or we can choose this bit. If we choose the right hand side, we get the green curve as the inverse function. If we choose the left hand side, we get the purple curve. So suppose that I choose x is greater than or equal to 1. Our inverse function will be 1 plus the square root of 1 minus x. And in this case, the domain is x such that x is less than or equal to 1, and the range is y such that y is greater than or equal to 1. Now there's such a thing as a self-inverse function. And that's where we do the inverse and we end up with what we started with. If a function has an inverse and the function itself is symmetrical about the line y equals x, then it's called a self-inverse function. Now the most obvious example is y is equal to x, and that's called the identity function. But y equals 1 on x is also a self-inverse function. Okay, that's it for this lesson. Our last lesson for this topic is on rational functions.